Okay, there it goes. Okay. So everybody, if you don't want to be in the video or your face in the video, don't turn on your video. So we're gonna get started with the lecture 18, polyprotic acids and weak bases. So first question, what is the pH of a 1.35 molar solution of H3PO4? If the first Ka value is 7.1 times 10 to the negative 3, Ka2 is 6.3 times 10 to the negative 8, and Ka3 is 4.2 times 10 to the negative 13. Okay, so these questions can get kind of long. You shouldn't see more than one question on the test about this. Okay, so first we'll start off by writing the expression of or the ionization of H3PO4 or phosphoric acid. This should be sorry, they're both aqueous, sorry. Everything except for water is aqueous all the time for these kinds of acid dissociation problems. Okay, so now you can make your ice table because you're given the concentration of H3PO4. So this one's probably going to take a lot of space. ICE and 1.35 m for phosphoric acid, and that doesn't matter. Get 0 here, 0 there. So it's going to be your change is going to be minus x. So this is going to be 1.35 minus x plus x and x and x. Okay. So your expression or Ka1 is going to equal x squared over 1.35 minus x. And Ka, you know, the first one equals, you could rewrite it like this. In this case, your Ka value is not greater than 4 magnitudes or less than 4 magnitudes in relation to your concentration. So you're gonna have to use the quadratic equation. Okay, so if we write this out and multiply both sides by this denominator here, you're gonna end up with 1.35 times 0.0071. And feel free to work it out as I go through. And that way, if you have like any questions, you can know immediately that, oh, I can't solve this on my own. Okay, so now you can rewrite this. Did I do that right? Yes, I did. Now you can rewrite this as and you might have chosen to subtract x squared instead of subtracting the other side. I like the other side because I just prefer having a positive a value, like not having a negative for the whatever negative coefficient, not coefficient, yeah, coefficient. For x, I don't like having negatives there. So, but either way, you should still get the same answer after you're doing the whole quadratic formula. Okay. And that equals 0 technically for the formula to work. Okay, so formula is minus 4AC over 2A. Okay, So negative 0.0071 plus or minus the square root of, and I'm just gonna do the whole term here. I'm gonna write the whole term under the radical to save space / time. Okay, so 0.038. And if you guys catch me in a mistake, please let me know. Or even if you just don't know how I got somewhere. Okay, so if I work this out, and I am rounding, we can ignore the x at the bottom. Sorry, I didn't see that. In this case, no, because the Ka value is not less than 4 magnitudes in relation to the concentration. It's not small enough for you to ignore it. So that x, you can say that in this case it matters. So you don't ignore. You don't just ignore it. Yeah. Okay. So take the square root of that. Okay, so you got negative 0.0071 plus or minus 0.19 over 2. You're going to get 2 answers. Okay, so 0.09. And then I'm not going to do the second answer because it's negative. 4 magnitudes means that it has to be less than, if you were, the difference between them, like if you were to divide one by the other, it should be greater than times 10 to the 4 power, or times 10 to the negative 4, depending on which one you put on the numerator and the denominator. So if I were to take if I were to take 1.35 and divide it by 7.1 times 10 to the negative 3, the difference between them is less than times 10 to the negative 4. I mean, times 10 to the 4. So I can't just ignore that. That's what it means by 4 magnitudes. Cool beans. Okay. So yeah, I'm not going to do the other, like 0.0071 minus 0.196, because I know it's going to be negative, and you can't have negative x value. That doesn't make sense, because that means you're gaining concentration for the reactants and losing concentration for the products, and that can't happen. So your x value is 0.09. So now you can go back. And so now you know that this one is a little long. I made it long on purpose because I want to give you guys practice. So the concentration, I'm only going to focus on the H2PO4 concentration, or no, I'm going to focus on both because of the thing that you have to do. Okay. So H2PO4, anyways, they're going to be the same anyways. So H2PO4 minus equals X. So its concentration equals 0.09. I'm going to go ahead and do the H3PO4 too, because no, I'm not going to do it because that's a different problem. Sorry. And your H3O plus concentration is 0.09, and that is molar. Okay, so you're not done yet because H2PO4 is also going to dissociate. So you got to do another ice table. Again. Okay. So H2 H2PO4 minus plus water gives you HPO4 2 minus plus H3O plus. They're both aqueous. I keep forgetting to write that. So what is your concentration of H2PO4? You calculated that in the previous reaction. So you know, let me first write ICE. 0.09 molar. This is not applicable. 0, and you start off, well, no, that's not true. And 0.09. So you already have some H3O plus, technically. And then so it's going to be minus X. Here you have 0.09 minus X plus X plus X, X, and 0.09 plus X. I think when I originally did it, the main thing that, like, when I took this course, I think I forgot that 0.09 is there. But it's there. Don't forget it. And then your Ka expression for the second one is, oh, I didn't write the expression for the first one. I'm actually not going to write the expressions, or I like the expression, but I will do the, like, write it out like this. And that would equal the Ka value, which is 6.3 times 10 to the negative 8. Okay. So this one is not so bad. Okay. So first you got to get rid of this denominator here. Well, not that. Don't get rid of that. But you got to get rid of this denominator by multiplying on both sides. And if at any time you're kind of like, if I go through, I'm probably only going to do the first base example just to save time so we can really get to practice this. This is taking longer than I expected. But it's just like, if you guys want to go back and go over it, extra practice could never hurt. Oh, sorry. That's what I was going to do. Don't multiply that at the bottom. Please don't. You can ignore it because the Ka value is so small. I was like, it can't be this difficult. Okay, yeah, you can just ignore it. So you can rewrite this as X, even the plus X, both of them. Because it doesn't make sense to get rid of the bottom one out the top one, or plus X but not minus X. Okay, so there's something that's going to happen here. This is going to cancel. Because 0.09 divided by 0.09 is 1. So your X is going to be equal to 6.3 times 10 to the negative 8. Okay, so now you can do your HPO4 2 minus concentration equals X, which equals 6.3 times 10 to the negative 8. And now your H3O plus concentration equals 0.09 plus X, which is roughly still 0.09. I mean, if you want to go all the way out, feel free to, but I will not. Okay, but it's still not done because now HPO4 2 minus is going to break down again into PO4 3 minus, into the phosphate ion. So Okay, so your concentration, ICE, your concentration of HPO4 is 6.3 times 10 to the negative 8. That doesn't matter. You get 0, and you have still about 0.9. So minus x plus x and plus x. And now you have 6.3 times 10 to the negative 8 times x, and 0.09 plus x. So now your third Ka value is 4.2 times 10 to the negative 13. Equals x times 0.09 over 6.3 times 10 to the negative 8. So now to solve, you have 4.2 10 to the negative 13 times 6.3 times 10 to the negative 8 divided by 0.09. So x equals 2.94 times 10 to the negative 19 molar. Or, yeah. So your P, or your phosphate ion concentration, negative x in the denominator. Your Ka value is super small. It's times 10 to the negative 11. So it's one of your tricks. You're just going to ignore it, the minus x, because, yeah, you don't. It's really small. So your PO4 concentration, x, so it's 2.94 times 10 to the negative 19. And your H3O plus concentration is, it's 0.0 or 0.09 plus x, which is still roughly 0.09. So that's the thing about these polyprotic acids. After the first dissociation, for the most part, it doesn't really do much. Like the dissociation of the other acids doesn't really affect it, because having like a Ka value, the first Ka value was times 10 to the negative 3. It's a weak acid, but it's not that weak, you know? So even then, still, like, only really the first dissociation affected the pH. So if you were to solve for the pH, it would mostly be very similar to whatever the pH is after your first dissociation. Now, the majority of the time, the reason why you're going to have to do this is going to be because of the fact that you're going to be asked to find the concentrations of the other ions, not necessarily the pH, where in this case you're finding pH. So, and in your pH in this case, so pH is going to be 1.05. So and if I had added all of the other stuff, it would have been like, I'll try it, why not? It's still 1.505. So it didn't change, it changed almost like not at all. So that's your answer, because the question did ask for the pH. Again, with these long questions, please like make sure you actually like, after you solve it and you're like, oh, I got X. So like if they're asking for X, like make sure they're asking for X. If they're not, then you just like you didn't finish. Okay, so you have another, this one you guys talked about a lot in the previous lecture. Okay, so you have a 0.53 HOBr solution, and it's asking for the percent dissociation if the Ka value is 2.0 times 10 to the negative 9. Okay, so the first thing to always do is HO, or is your expression. So HOBr plus water OBR minus okay. So I see and 0.53 m. That doesn't matter. That doesn't matter. And then 0, 0 minus x plus x plus x. So you get 0.53 minus x and x. So your Ka equals x squared over 0.53. And you ignore the x again because the Ka value is greater or less than times 10 to the 4 in relation to the concentration. Okay. So 2.0 times 10 to the negative 9 equals x squared over 0.53. Okay. So 2 times 10 to the negative 9 times 0.53 gives you. So x squared equals 1.06 times 10 to the negative 9. So x is 3.26 times 10 to the negative 5. Some more sticks. Okay. So from this, you can find your H3O plus concentration equals x, which equals 3.26 times 10 to the negative 5 molar. Molar. And OBR minus is the same. And your HOBR which is roughly still like 0.52997. Okay. So if I'm not mistaken, percent dissociation, you're gonna use this is, let me. H3O plus concentration over the original HO or HOBR. In this case, because they're so similar, it doesn't matter. But for like further problems, it is the original because you're trying to see how much it dissociated from the original concentration. So like, let's say if your Ka value was larger and it dissociated more, you have to take that into account. Like you can't just use the equilibrium concentration, you have to use the initial acid concentrations. Okay. And this is times 100. So that's 3.26 times 10 to the negative 5 over 0.53. So you get 6.15 times 10 to the negative 5 times 100%. So it's about 0.006%. So it doesn't dissociate very much. So pretty much the smaller your K constant is, the smaller your percent dissociation is. So this is your answer. Okay. So I think I'm only gonna do one of the base problems because pretty much they're the same. One of them just gives you KB, the other one's PKB. So let's just do this first one that I see. Okay. So what is the pH of a 1.1 solution of NH3 if it has a pKb of 4.75? Okay, so first things first, if you want, we can solve or figure out what the Kb is, because Kb is more important than pKb in this case. So 10 to the negative 4.75. Oh, let me write it out. So your Kb is 1.78 times 10 to the negative 5. Okay, so now we can do your ice table. And remember with this that you have to end up, because it's giving you NH3, that means it's a conjugate base. If they give you the pKb value, that means whatever they gave you is a base. So you cannot get an acid from it. So it's not going to dissociate into its conjugate base and then acid. It is the base. It's going to dissociate into a conjugate acid. So keep that in mind. NH4 plus OH minus. Okay. Now you can do your ice table. So you start off with 1.1 molar, that doesn't matter, 0, 0, minus x, plus x, plus x, 1.1 minus x, x, and x. Make more space. Okay. So your pKb right there is going to be 10 to the negative 5 equals x squared over 1.1 minus x. And you're solving for x, and that's going to give you your OH minus concentration, which you can do something with to determine your pH. Okay? So in this case, you can ignore the minus x, because the difference between 1.1 and 1.78 times 10 to the negative 5 is greater than 4 magnitude. You can ignore it. So that makes this a lot easier. Okay, so now you have x squared equals 1.96 times 10 to the negative 5. And that was just me multiplying by 1.1 on both sides. So square root. So x equals 4.42 times 10 to the negative 3m. And that is your OH concentration, or that will give you your OH concentration. So there's something that you can use to go from your OH concentration to your H3O plus concentration, and that is your Kw. So you know Kw equals H3O plus times the OH minus concentration, which equals 10 to the negative 14. So solving for H3O plus concentration, gonna be 10 to the negative 14 divided by 4.42 times 10 to the negative 3, which is your H3O plus concentration. OH minus concentration. So you get 2.26 times 10 to the negative 12 molar. And solving for pH is just the negative log of H3 H3O plus, which is oh, sorry. Scientific notation confuses me. 11.6. At first I thought it was like 0.6, okay, or 0.1. So this is your pH. It should be basic because your OH concentration is 4.42 times 10 to the negative 3. And your H3O plus concentration is 2.26 times 10 to the negative 12, which OH is a lot greater. You have a lot greater concentration than H3O plus. So that's the end of, that's all I'm gonna do for this worksheet. The last problem is very similar, except it's one step less because you don't have to convert from KB to KB. You just have KB. So I'm gonna start with the practice test 3A. If you guys have any recommendations, like for questions that you want to go on, please message in the chat so that way we can just skip to those instead of going in order. But until further notice, I'll just go in order. And I have the answers up on here because it's there. I think there's no point in me just like not having them up and switching between the two. I'm just working them out and giving also giving explanations. So for question 1, which of the following would be the strongest acid? The reason, so if you go through, it's important to note what your H is attached to. So, or the H that is going to be donated or lost in the reaction. So for A, your H is connected to C. For B, it's connected to O, C is N, D is S, and E is S. So two things that are important that determine the strength of an acid is one, your electronegativity, and 2, size. And oftentimes, more often than not, size trumps electronegativity. That's why HI is a stronger acid than HF, even though F technically has the greatest electronegativity. It's because of the size. Bigger atoms want their electrons more. So they don't really care. They're just going to give up the H. So that's why Se is going to give up its electrons. Se is largest. It's the largest of all of these. Yeah. So that's why this is right. So if you go by size of Se is greater than S is greater than O is greater than N greater than C. So if like you were looking for the strength of your acid, CH3 would be very weak. Like it's not really going to give away an electron very easily. Hydrocyanic acid for 2, you kind of just have to know that one. It's hydrocyanic acid. It's because CN is cyanide, and cyan is a cyanate ion, I think. I don't know. I'm pretty sure. So this is one that you would just have to kind of memorize. For 3, at equilibrium, the H2 concentration is 0.002, I is 0.002 or 0.022, and HI is 0.10156. So what is the value of Kc? This one is just your Kc is equal to your product concentration, which is HI, squared over your reactant concentration This is just you putting it all together. I'm not necessarily sure if you guys want to see me work it out. It's just you plug in these numbers to there. That goes there. Oh, sorry. Those arrows are not right. Here, this goes there, that goes there, and you'll get the right answer. Okay, so which solution has the greatest percent ionization if each solution is 1.0 m? I said this in the previous worksheet. Oh, can I explain number two? This one is you just have to know the name. There's no like easy way. If you know that, I'm pretty sure it's the cyanate ion. If I could find my phone, I'm pretty sure it's just the cyanate ion. So, like, you look up CN minus. Or cyanide. Yeah. So this one personally, this one trumps me up a bit, or it always did, because I usually just assumed that the hydro prefix was reserved for whenever it was just H bonded to just one other atom. In this case, hydrocyanic acid is unique because it's not like that. So this is one that you would just have to know. So, going back to 4, I explained this in the previous with the other worksheet that the greater your Ka value, the more it's going to dissociate. So just like before where you had a low Ka value, so if you have a small Ka value, you're also going to have a really small percent ionization. So that's why E is the correct answer, because of all of these, it has the greatest Ka. So higher, it's greater than all of them if you look at the Ka. Okay, so in a reaction vessel, 0.75 atm of I2, 0.75 atm of Br2 are initially mixed. Once the reaction reaches equilibrium according to the reaction below, what will be the partial pressure of IBr? Okay, so this is just another ice table. So I2, Br2. Yeah, partial pressure. Don't get too stumped by those. It's just like the same thing. Because it's just saying that not only IBR is in there. So essentially, it should be an equilibrium reaction because the only thing that's in there is it's not only IBR. So it's a mixture of different things. So it's like, I guess if they give you a KP, chances are you're going to use it. Or any of the Ks, chances are you're going to use them. So 0.75. And this is just going to be a quick one. This case, your Ka is pretty big. Plus 2x. So hopefully this lets me make space. Okay. So you get 2x squared over 0.7 x also squared equals 117.6. So this one, you're lucky. You got a square at the top and the bottom. So you can just square root both sides. So square root of 117.6 is, sorry, so 2x over 0.75 minus x equals 10.8. I still need more space. Okay. So I move the 0.75 minus x onto the other side, or multiply by 0.75 minus x on both sides, I get 8, 1, 3. Sorry. No, yeah. So I can just solve. So just gonna, in order to solve, just add 10.8 on both sides, 10.8x on both sides. You get 8.13 divided by 12.8. So your x is going to equal 0.64. Or in this case, it's gonna be prettier if I do 0.64. And this is gonna be ATM. So your IBR concentration is 2x, which is 2 times 0.635, which is going to equal 1.37 ATM. 8.13 is just when I multiply 7.5 minus x on both sides, is going to be 0.75 times 10.8. That makes sense. So these numbers multiply together. That's what 8.31 or 8.13 is. Okay. So for question 6, what is the Kp of the following reaction if the Kc is 5.31 at 723? Okay. So the Kp Kc formula is Kp equals, sorry, Kc times the change in moles. Okay, so it's important to note phases. Phases are always important. So you're not going to use this, the U308, I think. You're not going to use that because it's a solid. So it doesn't go into it doesn't go to any of these calculations. You don't use it. Don't use it. So looking at when you go to solve for your change in moles, make sure you only use moles of gas or moles of aqueous solution. Like, you don't use solid. If you use solid, it's going to be wrong. Because if you use solid, I even made this mistake myself. You would have gotten E. That's not right. Not the right answer. Okay. So Kp equals 5.31 times, and this one you're going to use the 0.0821 times your temperature. Make sure it's in Kelvin. So 273 plus 723, 996 Kelvin. No, I'm not going to use units. Save time. So I use units for one thing. I have to use units for everything. And your change in moles, you have 3 moles on the product side. You write it out, actually. 3 minus 4, but your change in moles is -1. So it's to the -1 power. The beginning of the question, for this question, make sure you pay attention to the phases. The phases matter. So if it's not a gas or if it's not an aqueous phase, it doesn't go into your change in mole calculation. So that's why I crossed out one of the the products, because it's not aqueous or gas, it's solid. And you don't use solids at all, or solids or liquids. It's only gas, only aqueous. So that's why you don't factor it in to your change in mole calculation, because it's only the change in moles of concentrations that could actually change at equilibrium. The solid concentration is not going to change. So if you do all of this, you're going to end up with that answer, I promise. All right. So hopefully that answered your question. So for question 7, so consider the equilibrium reaction below. More O2 gas is injected into the reaction vessel after equilibrium is reestablished. Which of the following values is lower than the original equilibrium value? Which of the following is lower than the equilibrium value? Oh, sorry. I was reading SO3. In my head, I was like, this doesn't make sense. Okay. So you might be asking, why is it not O2? Because technically, you're going to inject O2 inside, and its concentration is going to decrease, but it can't decrease. It's kind of not possible for it to decrease once you've added some in there. It's going to decrease after, it shifts back to equilibrium, but it's not going to be lower than its initial. You're not going to get lower amounts of O2 when you've added O2. It's just not going to be as much as you initially added. The difference or what's going to change is your SO2 concentration, because SO2, some of the SO2 is going to have to react with the O2, the added O2, to form SO3, but you didn't add any SO2 into there. You only added O2. So because it has to react with O2 in order to reform or form more product or reactant, sorry, it's going to decrease. It's going to be the only one that decreases, because what's important is the ratio more than just how much of each one that you have, because it's not just the individual concentrations that matter. It's the ratio that's more important. So since it's going to be SO3 over, what's important is whatever number this multiplies to, not necessarily what this number is and what this number is. If this ratio needs to be 1/4, I'm not going to be 1/4. That's not a good example. Let's do something like 1/20. So let's say initially this is 4 and this is 5, but you add more O2 into it, but you still need to do something to maintain this ratio. This concentration can shift, the SO2 concentration can shift where it's 1/2 times 10, just as long as the ratio is still the same. It doesn't necessarily matter the fact that it has to be at equilibrium, it can still be lower just as long as the concentration of both reactants equals the same number, or it's equal to the same number or same ratio. The ratio is preserved. If that makes sense. I hope it does. It's like hard to explain. And I feel like sometimes when I put numbers in, I make it more complicated. Yeah, partial pressure of O2 would then be lower because like it would just switch. So it's like so you would say that now the SO2 concentration could be 10 and the O2 concentration could be 2. Just as long as this ratio, this 1/20 ratio is preserved, that's fine. Because think about it, you're adding O2 and it's going to cause a shift back to the SO3. So in order for it to shift back to SO3, SO2 is going to have to react as well. And that you didn't add any extra SO2. So it's going to, you're just losing SO2 in the process as it goes to SO3. That makes sense. Hope that makes sense. Okay. So the value of the equilibrium constant for the reaction. So you got 2 HBr goes to H2 plus Br2 if the Kc equals 1.26 times 10 to the negative 12 at 50 K. What would be the value of the equilibrium constant, Kc, for the reaction? Okay. Oh, for the following reaction. Sorry, I didn't look at it. Okay. So what you did was you took everything and you divided by 1/2. So whatever you do to the concentrations, you have to do to the K constant, except it's slightly different because you don't multiply the K constant by 1/2. Don't fall into the that trap. What you're gonna do is raise your K constant to the 1/2 power. And like, I guess if I were to write it out as to like why, so you have HBr H2 to the 1/2 Br2 to the 1/2. This is the square root of, so the square root of, let me erase that. So like if you ever get confused, I would say just write it out. So you can see that, or write out your expression. So you can see that this is the square root of this. So this here is the square root of this. So you take your K constant and you take the square root in order to get that. Yeah. I'm gonna verify. Huh. At 50 Kelvin. Oh, sorry. And then you have to invert it, because technically it's not that. Because this is your original here. Well, no, this is the new one. So invert that as well. And this should not be this. So it should be. So take the square root and then take the inverse of it. And you get B. Sorry about that. Oh, sorry. That was my eraser. Accidentally erased part of it, I think. Unless I did it and I just wrote it wrong. But yeah, it should be 1. Okay, so the pH of a solution at 25 degrees Celsius, in which the OH minus concentration is 3.4 times 10 to the negative 5. So you can find your H3O plus concentration by taking 10 to the negative 14 divided by your OH minus concentration. So you take 10 times 10 to the negative 14 divided by 3.4 times 10 to the negative 5. You're going to get 2.94 times 10 to the negative 10. And you take the negative log of that. So negative log of H3O plus gives you 9.5. That should be molar. Okay, so which of the following will not give an acidic solution when dissolved in water? This is important. Pretty much it's because if you dissolve K2O in water, you're going to it was metals, and metal oxides are basic. And what equation? Oh, it's your Kw. It's the same as so your Kw equals H3O plus times OH minus. It was just reworked. So instead of having this, I did H3O plus is your Kw divided by your OH minus concentration, and your Kw is just times 10 to the negative 4. I mean, negative 14, sorry. That's how I got that equation. Yeah. So, yeah, I think your metal oxides they are bases in water. Or they are basic. No, they're basic. So it's going to, this is always, yeah, it's basic. So it's going to form a base in water, if that makes sense. Whereas your non-metal oxides are going to form acids in water. So like if you know, like if you guys are familiar with your strong bases, like KOH, NaOH, these are metals, the K and the Na. Whereas if you have H2SO4, if you're familiar with HNO3, these are acids. So that's a good way if you like forget. If you remember your acids versus bases, acids usually involve non-metals and like non-metal oxides, whereas bases are usually metals. That makes sense. They don't have to be, but they tend to be. Like you just remember, because I know it's hard to remember like every acid and base. But if you can remember your strong acids, even though H2SO4 is not a strong acid, or is it? I think it is. But if you remember your strong acids, strong bases, it can help. Like you remember, like from all of these, you can get an acid like H3PO4, H2CO3, so on and so forth. Whereas KOH from. Okay. So consider the following reaction at equilibrium. If C2H6 is added to the system and the Q value is calculated, which of the following is true? The reaction will move to the left. That's because you're increasing this concentration. So your reaction is going to go there. So it said that it was at equilibrium. So that's like the key. It's already at equilibrium. So you disrupted equilibrium by adding more products. So like your Q is C2H6 over C2H4 times H2. So now this number here, the C2H6 concentration is going to be too big. So you're going to have to create more reactant in order to maintain equilibrium or to go back to equilibrium. Okay. So which of the following reactions does not proceed significantly to the right in an aqueous solution? So does not proceed to the right. Oh. This one can kind of be if you know acid strength. Whereas you're always going to proceed to the weaker acid, if that makes sense. So that means that H2SO4 is stronger acid than HSO4. So a stronger acid is going to want to donate its H. It doesn't want the H. It wants to give it away. So you're more likely going to go from H2SO4 to HSO4 because of the fact that H2SO4 is a stronger acid than HSO4. Whereas for CH, this reaction is not really going to happen because if the H2SO4 Ka value is greater, yes, greater than your HSO4 value. So it's a stronger acid. So it's going to want to proceed in the reverse reaction. It's not really going to want to form H2SO4 because you don't want to form the thing that's going to want to immediately go back or proceed back because it's a stronger acid. So it wants to donate its H. It doesn't want the H, if that makes sense. So that's why C is correct. I'm not sure if you guys went over Ka values and or like how intuitive it is for you guys to know like this. Yeah, I'm not sure how if you guys really went over this in class. Okay. So HNO2 has an acid dissociation constant of Ka equals 4 times 10 to negative 4. What is the pH of a 0.25 solution of NO2 minus? Okay, so this is going to require your friend the ice table. Before I move on, I think I'm going to stop the recording.